Hello. All right. Let's get you some examples with concentrations. So, just to recap, concentration has to do with how much stuff you dissolve. Um, we typically do make lemonade, and you take some amount of powder and some amount of water, and you kind of have a sense of what you like already. Um, and if not, that's totally cool. You can learn from people around you. Um, and the whole idea is that you can have different amounts of stuff dissolved into a solution. So the person next to you might have a solution with tons more stuff dissolved in it. You can usually see this visually. It's like a darker shade of yellow, if you're looking at lemonade. The person on the other side of you may like more water and kind of like the hint of the flavor without being like overwhelmed by the flavor. Um, all of these are awesome, right? Like the whole purpose of this thing is that we're all different, and through that we can see that depending on what you prefer, you make a different concentration of your actual beverage, your actual lemonade. Um, so if there's less lemonade dissolved, it's gonna look lighter, clearer. If there's more lemonade dissolved, it'll have a darker color. Um, I imagine none of this is particularly surprising to you. Uh, the stuff that you may not have seen before, um, you have seen food labels. So all of the stuff on your food label, um, we often will do this whole lemonade thing and then say, what's your favorite soda? And somebody, will get like whatever, Sprite, Coke, Dr. Pepper, like choose one. And then we look up the, what do you call it? Not ingredients, not recipe, the thing with the numbers, the nutrition label. So I'll look up the nutrition facts of something, right? Like usually favorite soda. And then we figure out the concentration of sugar in that soda. So this is not a terrible idea because it will actually help you with all of the other things also. I was just going to take you into the kind of the nitty-gritty math. Let's just say Coke. That's a pretty classic standard here. Nutrition facts. Alright, Coke nutrition facts. And we've got for and concentrations are all about I just realized this is maybe not the best idea for a different reason, but it's all about how much solute, how much stuff, and we'll measure that in moles of solute relative to how much liquid, and we'll measure that in liters of solvent. So for example, in your Coke, your nutrition label says how much sugar. Coke has 44 grams of sugar. We want that in moles. For the sake of time, I will give you that. Sugar is C6H12O6. It's got a molar mass. We're going to convert those grams of sugar to moles of sugar. To solve for moles of sugar. Sugar has a molar mass of 180. You take enough bio, you just get to know that. So how many moles of sugar are in a can of Coke? Find your calculator. Get 44 over 180. 2.4 moles of sugar in a single can of Coke. Let's do water. Actually, this is a good idea because you know what Coke is. And so here's going to give you like a moles per liter kind of concentration that you actually know. Okay, this is looking at this particular nutrition label. Is looking at 1 cup of water. Let's do a quick conversion because we want liters. I do not know that one off the top of my head. Luckily the internet does. 1 cup is 0.2366 liters. And to find your concentration, your molarity, you're going to take moles of solute divided by liters of solvent. Here we've got 0.244 moles of sugar. And 0.2366 liters. This is interesting because this is going to be about 1. I wonder if this is like fountain soda versus soda in a can or something like that. Anyways, find your calculator. You've got 0.244 divided by 0.2366. Rounding could get you a slightly different number. I rounded both of those. And the molarity, the concentration of sugar in Coke is about... How many sig figs did we start with? We started with 2. So I'll keep 3. I should keep 2, but somewhere around that moles per liter. There's 2 ways to write this unit. You can write out moles per liter, moles of sugar per liter of water, or you could condense that whole unit like this and say, here's our molarity. Our molarity is about 1.03 molar. That capital M means moles per liter. So it's got a molarity of about 1.03 molar sugar. And if you don't specify, it's implied in water. So your Coke gave you nutrition facts in grams and cups, part British, part metric. And what we did was we converted the grams to moles, we converted the cups to liters, and took that ratio of moles per liter to figure out the molarity, the concentration of sugar in your Coke. So Coke has about 1 mole of sugar per liter. Another interesting thing about molarity and concentrations in general is that any sip of Coke is going to have about the same concentration. So you could have a bathtub full of Coke. It would have a concentration of about the same molarity. You could take a teaspoon out of that bathtub. It would have about the same concentration. You could take a sip. It would have about the same concentration. You could drink the entire can. It would have about the same concentration. Because the particles are evenly distributed throughout, like at the point you have a solution, the particles are evenly distributed. You can take any volume and it'll have about the same ratio of stuff inside. Yeah, so a tanker truck full of Coke would have the same concentration as a drop inside of that tanker truck. So it doesn't matter the volume. What does matter is the ratio. If that doesn't make sense, don't worry. The math still works exactly the same. It's a ratio of how many moles per liter in that thing. Let's do one example from your actual question page. Okay, here's your actual question page. If you're in the packet, you're looking for this one. I'll link it as always. This is page 76 in your packet. Yeah, we are going to do number 1 all together. we are going to skip number 2. Number 2 has this word that we're not going to worry too much about that. Don't worry about that. That just means add more water. So you find the number of moles, you find how much more water, but we're not going to worry about that. So we're going to do number 1 together. You're going to do number 3 on your own. They're going to match. Off we go. Explain how you would make a 450 milliliter solution of a 0.350 molar sodium hydroxide solution. Okay, so things to notice. You're starting with a volume. So this is solutions number 1. You're starting with a volume, and you've got this capital M. So this capital M means moles per liter. Okay, here we go. Start with your volume. So 450 milliliters. Here's a clue. We're trying to find moles. We have this conversion factor of moles per liter. You're going to take your milliliters into liters. And then you're going to use this molarity conversion factor because you know how many moles for every liter. You don't need to know how many liters because you know the molarity. You know how many moles per liter. Your final step here, I said moles, but if you're going to make this thing on a scale, you actually really want the units of grams. And that'll get you grams. Grams you can put on the scale. And in that final step, it says how do you do this? How do you make it? You're going to say we mix however many grams into however much we started with. So here we're starting with 450 milliliters of water. So this whole mumbo jumbo is to figure out how many grams of sodium hydroxide we would need to get a 0.35 molar concentration in 450 milliliters of water. Okay, we only want 450 milliliters. There's 1,000 milliliters in every 1 liter. We've got our molarity right there. That molarity means that many moles in 1 liter. Pick that up, plunk it in down here. We want 0.35 moles for every 1 liter. In this final step, got sodium hydroxide. You want to put your sodium hydroxide on a scale, so let's figure out its grams instead of its moles. Find your periodic table. Sodium, I think, is 23, oxygen is 16, and nitrogen is 1 gram per mole, I think. Actually, I don't think I knew. Okay, so sodium is 22.99. We're just solving the molar mass right here. We've got grams to moles, molar mass, sodium, oxygen hydroxide, 22.99. Oxygen is still full at 16. Nitrogen is 1.01. So your total molar mass for sodium hydroxide, that's how many grams per mole. This is week 3 stuff, if that just was like what just happened. Week 3, I think Tuesday is your molar mass stuff. And then Wednesday gets you converting. So if you're like, how did this moles to gram thing just happen? Wednesday of week 3. That's your key. Once we find our molar mass, plug it in using the units, 40 grams per every 1 mole. And you're all set up. Off we go. Find your calculator. 450 times 0.35 times 40. That gives you a number on top. Divide that by 1,000. Divide that by 1. Divide that by 1. We've got... Okay, so to make the solution, to make your 0.35 molar solution of sodium hydroxide, 450 mils of your 0.35 molar sodium hydroxide solution, we just solved for grams, so you mix 3.6 grams of sodium hydroxide into 450 milliliters of water. And that gives you a 0.35 molar concentration of that solution. Okay. Try that same deal on number 3. Number 3 is going to look strikingly similar to number 1. Skip number 2. I'll post this PDF for you. I think you got this. Yeah, cool. That's concentrations, both the concept, some examples, and if you're making solutions, how to do that. How to figure out how much you actually want in your bottle at the end, how strong you want it, how concentrated you want it, and how to do your math to figure out how many grams of your solute you're going to measure out on your scale to mix with that amount of water. This is the kind of thing that you use all the time. If you work in a lab, you will do this constantly because you're constantly using your stock solutions and you need to make more. So like anytime you want to make 0.35 molar sodium hydroxide solution, you're probably making a whole lot more than 450 mils, but let's say you're just doing 450 mils. You do some math, pull how much sodium hydroxide you're going to weigh out on your scale, mix it with your water, and that's your solution. Alright, go and try number 3. Enjoy.